Hello everyone, thank you for joining me here today. And I'd like to start off with a question. Have everyone taken some kind of medication before? I see a lot of nods. I probably would see a lot of nods if this was a real audience. But I would be probably safe to assume everyone have taken some kind of medication, be really over the counter, some kind of allergy medication, a heartburn medication, even the pain medication. I certainly have. But have you ever thought about how the new medications developed? And this is what I'd like to answer today. I'm sure you probably didn't know this information, but a medication takes about 10 years to develop once it gets from the lab to the consumer, and about $1 billion to be spent. Many drugs in the past, they were found by pure accident or by modifying or deriving from organic compounds like plants, etc. But today there's a more efficient way to design a drug. That's computational chemistry. So what is computational chemistry? To take you a little bit back, about 2,500 years ago, to the Greek philosophers, which probably held a sandwich in their hand and looked at the piece of cheese in there and thought, well, what if we take this piece of matter and if we cut it so many times, there has to be a particle that you can't cut any further. They call that atomos, an uncuttable or indivisible particle. That's hence the atoms. That's where it came from. So you think 2,500 years later we'd probably be very, very efficient and know what's going on, but not so fast. About 2,300, since their idea was just pure guess, we needed some practical, some experiments to confirm it. And it's not until 2,300 years later, like scientists like Dalton and Antonio Lavoisier, they were able to describe atoms and describe their general behavior. And from there, scientists started doing more research, and they found out the atoms were not even the smallest particles. There were smaller ones, the electrons and protons. And the work of numerous chemists and physicists, it was confirmed. But then there's another question. So how do these protons and electrons, how do they behave? And that's where scientists like Bohr, Rutherford, Planck, and Einstein, they came up with an idea, or excuse me, with well, not an idea, more like a model of mathematical model how both of these behave in the system. And Bohr, he called this system a planetary model. He said there's a central nucleus and there's electrons that have their own orbital, which they spin around or go around the nucleus. At that time, that seemed like a very good idea, but now, of course, we know that was not it's not as good as it seemed. And scientist Heisenberg, he saw it, and he said that based on the type of experiments that was done by the chemists and physicists at that time for the experiment, he said that we cannot specifically say where the electron is at a certain time, because since it's spinning and we're using some kind of energy to measure it, we giving that electron some kind of energy, adding to its momentum and changing its location. So we cannot say with certainty where the electron is. He called this an uncertainty principle. Instead, he came up with the idea of quantum theory, which included or proposed that electron behaves like a particle and like a wave. Essentially, he combined those and said it behaves like both. And from here, that's where the quantum mechanics started. And what quantum mechanics is essentially, it's a mathematical equations or set of mathematical equations that describes a cloud of the or electron cloud around the nucleus where you would most likely find the electron. And Schrödinger came up with the equation which would describe that cloud and describe its change within time around in the atom. Hence, we started the computation of quantum mechanics. So we can use the equations to describe or calculate and visualize the electron cloud around the water molecule, for example, here, and say, well, this particular region here has more electrons than this region here, since oxygen is more electronegative and hydrogen is it pulls electrons from hydrogen towards the oxygen. That makes sense. But then if we add more water molecules, they start to interact with each other by creating the by hydrogen bonding. Essentially, the positive charge in hydrogen gets attracted to a negative charge on oxygen, and that's where these bonds create. So we can use those properties. We can use the electron concentration and properties on the molecules to describe the relation between the two. Essentially, this is called the QSAR, or quantitative structure activity relationship. This is very important, or this is one of the ways the drugs are designed today, because we can take the physical property and use a chemical activity, or which would be some kind of biological activity within the body, to find the relationship between the two and find a more efficient subject. And I'll tell you how it's done. So to go a little bit back, an example would here be the cyclooxygenase inhibitors. Cyclooxygenase is an enzyme that's found throughout the body, and not until a while ago, about 10 to 20 years ago, we thought there's only one of them present. But now we know there is cyclooxygenase 1 and cyclooxygenase 2. They're different flavors of these enzymes. One is found in kidneys and stomach and intestine, and the cyclooxygenase 2 is primarily involved in the inflammation processes throughout the body, because it releases prostaglandin. So when we were treating somebody with arthritis with aspirin or ibuprofen, for example, the ibuprofen and aspirin does not differentiate between the cyclooxygenase 1 or cyclooxygenase 2 because it binds to both of them. So if you have an arthritis, the side effect of the treatment with aspirin or ibuprofen would have a damage to kidneys or ulceration of the intestine, and that's what you try to avoid by finding a different drug. So if we start from ibuprofen and aspirin and use the computational chemistry, for example, these two molecules here, and you can say these are pretty similar, except there is a variation in the major part, but we can also vary the smaller parts, which are depicted here as R groups. And we can vary their location on each molecule and see how it affects how it changes the biological activity within the body. Biological activity here is depicted as IC50. This is measured in the lab, in the actual wet lab, and we get these values by pure observation. But we can use them for future compounds, which is pretty important. So if we combine these, if we look at the location of these R groups, and we're trying to look at the charges on these molecules here, we can calculate those charges using computational chemistry. And then we can relate them, or we can use a linear equation, a simple linear equation, and relate it to a charge on the molecule. A charge on the molecule versus its activity in the body. If we correlate those two results, we will get something like this. So what you see here, this is a charge on the molecule carbon-6, and the biological activity of this particular molecule of the reaction with the cyclooxygenase 2. As you can tell, this is a very small correlation, because correlation ratio is only 0.25, and that's pretty small. We want to be above 0.6 or 0.2, but this is not unexpected. This was only a practice lab. Essentially, we wanted to know how this computational chemistry works, not really have any positive results. Although if it would happen, it would be absolutely amazing. But this is what was done by researchers in the lab in my practice, and we didn't find any correlation between the charges and between the activity of these molecules. But the researchers in the lab of Celebrex, they did find that correlation. So they found this molecule, and what you see here is the molecule of Celebrex, which is tightly bound to, well, tightly interacting with the molecule of the cyclooxygenase 2. And as you can tell, for the simplicity, this is only depicts the visible or only parts of the enzyme that interacts with the molecule. So what is computational chemistry? Computational chemistry and drug research leads to more efficient and more potent drugs. It helps design drugs that are more powerful and more specific in their action, because they only acts with certain part and avoids the other one. Of course, there are other factors that have to be considered, and as I said, this only shows the starting position where a scientist begin for drug research, because you do have to take into account the solvents used, the byproducts in the body. So essentially, if drugs breaks part in the body, we have to consider what happens with those too before they excreted. So I hope this was very informational for you, because this certainly is. Medications are today designed more efficiently than before, and we use computers and molecular modeling to design new medications. And as you can tell, chemistry is not only mixing chemicals in the lab, but also involves a lot of computers and modeling work. And I hope I was able to give you a little bit of information how the drugs are designed today. If you're interested in if you have any questions on the information that I gave you, I will gladly answer the questions that you have if you leave them under this video. Thank you for your time.